I live in the US, near New York City, where we saw the beautiful taxi cab picture. I worked in industry for many years, and now I'm working in university. I'm on sabbatical here for 6 weeks in Brazil. I'm really thrilled about that. And I'm hoping to bring you a little bit of experiment and theory in the area of frustrated magnetism. Now, one of my goals in this is to give you a flavor of interesting problems that are being studied now that have links to other areas in physics. Okay? After all, one of the reasons we went into physics is that we love the notion of unexpected connections. And frustrated systems are really simple spin systems that you might think are very abstract. But what I hope to convince you of in the next few lectures is studying really simple systems sometimes can have implications far outside what you expect. Now let me tell you that I have worked on and off on frustrated magnetism. I did part of my thesis on frustrated magnetism ages ago. Recently I've come back to frustrated magnetism thanks to a collaboration I have. But what I thought I would do in these lectures is cover ground, not necessarily my own work, but cover ground that I think is really exciting. So in some sense, I have a little bit of an outsider's view on this, but hopefully I can transfer to you some of the excitement that I've had putting all this together. Hopefully some knowledge too, but mostly excitement. Okay, so what's the plan? Believe it or not, there is a plan. Okay, number one. The plan is the following. Today, we're going to start at the beginning. We'll do a simple introduction to frustrated magnetism, and then I'd like to tell you about spin ice. Okay? Spin ice is a beautiful system that was suggested, goes back to the ideas of Linus Pauling. It was suggested in the 30s. The ideas, then Phil Anderson at Bell Labs made some suggestions. Recently, it's been observed in the lab. And one of the things that I want to tell you about is that this is a system where the low energy physics leads to an emergent gauge structure and the possibility of magnetic charges. Okay? So we're going to talk about that today. Now, what I should say is, at the end, I'm hoping to give you a flavor. I realize it's the end of the day. I'm happy to talk about more details either in the discussion or after, but at the end of each lecture, I'll also give you references. So if you're interested, you can look up some of the things that I've talked about. Okay? Then, next time, which I believe is Thursday, we're going to talk about order from disorder. Okay? Normally we think of fluctuations as disordering systems. It turns out in frustrated systems it's counterintuitive, and frustration actually can select order. We'll give some examples. It turns out that some of the systems you heard about today, particularly the pnictides, have a lot of interaction with this second lecture, order from disorder. Okay? So we're going to talk a little bit about that, and hopefully that will interface with some of what you've been learning about pnictides. The last lecture, I want to talk about the elusive spin liquids. What are they, and have they been cited? Okay, so that's the plan. All right, so just to give you an idea again of what's to come, we'll have Antiferromagnet. This will be the plan for the first day. That's today. Then the second one. In the second lecture, one of the things that I want to tell you about is about the J1, J2 model, which you're going to hear about a little bit already in the pnictides. Okay, we're going to talk about how we get an emergent discrete order parameter, and then we're going to talk about some work that's ongoing with our collaboration in Karlsruhe. And in particular, we're going to talk about emergent criticality and, believe it or not, a link to gravity, the baby string theory. Okay, so that's what's the second one. As I told you, I've chosen topics. This is sort of a tapas of frustrated magnetism. I've chosen topics where I want to show you how studying a simple model can lead to results that are way beyond the materials that inspire. Okay, the last lecture will be on quantum spin liquids. I'll have told you about order from disorder. Now we're going to talk about disorder by disorder. We'll go back to the transverse field Ising model, and then we'll ask what happens when we have quantum fluctuations plus frustration. turns out that recently there have been some really exciting experiments that I want to tell you about, and they've inspired some numerical computational experiments where people have taken ideas from information theory, in particular entanglement entropy, to try and understand whether we can actually nail down the spin liquid. Okay? And then we'll end, of course, with some random open questions. So that's the plan. Okay. So let's start at the beginning, and let's talk about what we're going to say, what we're going to discuss today. And please feel free to interrupt me or ask questions, whatever. It's, that's what it's all about. So we're going to start with a brief history of antiferromagnetism. Then we're going to ask, what is frustration? And of course, we all know what frustration is. What do I mean frustration for spins? And you've already had a little bit of a taster of that in some of the earlier lectures today. Then we're going to apply some ideas that were originally due to Maxwell, James Clerk Maxwell, for elastic systems. We're going to apply them to spin systems to figure out which ones should we actually look at to get the maximal frustration. Okay? That'll end our section on introduction to frustrated systems. Then we're going to talk about spin ice. What is spin ice? Why is it interesting? And then we're going to talk about the possibility of magnetic charge in spin ice. Okay? So stay tuned, and at the end of the lecture you'll find out whether or not you have to relearn everything you know about electromagnetism. Okay? Now, I mentioned to you that I'm actually talking quite a bit about work that's not my own, and I'm very thankful to my friends, Leon Valens, Claudio Castanova, Robert Mersner, and Shivaji Sondi, for sharing with me some of their slides to really pretty pictures. Okay? So they've been very generous about that. Okay, so let's start at the very beginning, 4,000 years ago or so. Magnetism, like everything else, has a very colorful and inventive history. Legend has it that there was, at least in Western culture, legend has it that there was a shepherd called Magnus who was herding his sheep in an area of northern Greece. And he found that both his staff and his shoes were sticking to the ground. He didn't know really what to do, so what he did was he dug down, he found that there was a rock, and he called them lodestones. And now we know that lodestones contain magnetite, F2O4. That's right. F3, sorry. F3O4. Okay? Oh, I don't think it's that important, but it's Fe3O4. Okay. So, the point was that it was found by the Greeks, also certainly by the Chinese, also that there were certain kinds of rocks that seemed to attract other metals. Okay? And in particular, Pliny the Elder, who was about 50 AD, discusses how near the river Indus there were mountains of some sort of magnetite that attracted iron, and there were supposedly whole islands that would attract ships. Even the great mathematician and physicist Archimedes is reputed to have used a huge rock, I mean this really does sound legendary, to pull the nails out of a ship and to sink it for his country. Okay? So even then one had to do applied research. Okay, but in any case, so these are the legends around that. Okay? Interesting enough, some people realized, particularly in China, that if you floated a little lodestone, a needle of lodestone, in water, it would point in one direction. And so from what I understand, around 4,500 years ago, the Chinese were the first to develop marine compasses. Okay, so that's very nice. So ferromagnetism has been known, I hope I've convinced you, for a very long time. And ferromagnetism, though, was really studied, was mostly given all kinds of superstitious, wonderful, magical properties, except maybe by Archimedes, but who used it to get a little bit of quiet to do his real research. And what can we say about ferromagnetism? Well, ferromagnetism, of course, was studied by the Curies quite a lot. And in particular, in ferromagnetism, if you look at the susceptibility, which is the ratio of the magnetization over the field, what we find is the inverse susceptibility has a positive intersect. Okay? And that we call Curie, that's this constant C. Well, anyway, and one thing I will note also is that Pierre Curie was fascinated by magnetism, and this will be important later on. And he of course, knew about Maxwell's equations, and he was always wondering how come they're not magnetic charges. And he had this notion that maybe there could be magnetic charges in the magnetic material. Okay, hold that thought, we'll get back to it. All right. Now, in the early part of the 20th century, Niels Bohr, and also, interesting enough, a student, Henrika Johanna von Leuven, independently found that magnetism is solely a quantum mechanical effect. Now, first of all, as you might guess, Niels Bohr was already a senior researcher. Henrietta Johannes von Leuven at that time was a student. The fact that it's called Bohr-von Leuven theorem, I find a real testament to the fact that there are good guys out there, and Niels Bohr was one of them. He didn't just take it all for himself. He realized there was a student who did this work too, so hopefully you all will grow up to be these kinds of good guys. All right, so let me actually tell you intuitively what their argument was, okay? And I won't go through the stat mech of this, but basically the argument was as follows, that the energy is going to have a kinetic part and a potential energy part. That potential energy part is not field dependent, okay? Remember, at that point people said, suppose we have charges, okay? How could we get magnetism just by charges moving around, a la Ampere, okay? Well, if you have an energy that's half mv squared plus u, then the point is that the magnetic field does not contribute to the potential energy. We have the Lorentz force, which is Q E. Can you see this, or do I have to use the other chalk? Can you see that?
Sorry, I have a serious question here. So is this actually the ferromagnetism because we have C over T, not C over T minus Ty?
No, this is ferromagnetism right now. We're going to ferromagnetism.
Ferro.
Pardon? No, this is paramagnetism.
Okay.
Sorry, I was pointing to that to be ferro.
Okay.
Sorry. So what we have here is we have V cross B, and so therefore the rate of work is going to be F dot V is QE dot V, and there's no B dependence. So in other words, if B equals 0, at B equals 0, there's no net motion of charge, then at finite B, there can be no net motion of charge, and therefore, classical mechanics does not account for this. This is very intuitive. They, of course, solved it also using proper stat mech treatment, and you may have seen that in some of your stat mech classes. Well, that was actually very important because then Heisenberg, of course, when Heisenberg learned that quantum mechanics was important for magnetism, he stepped in and developed a model that you've already seen today in the context of the pnictides, the Heisenberg model, okay? And it's right there, and that's something we're going to be talking about a lot. Okay, but what about antiferromagnetism? Now enter shyly the antiferromagnetism. Why do I say shyly? Because Néel suggested that we have an up-down ground state. In the previous slide, there were many materials for which the inverse susceptibility went negative. Okay? And Néel and Grenoble at the time suggested that maybe something else was going on. Maybe one had a state that looked like this. Okay? And so it was proposed independently by Néel. Landau, though, the great Landau, had some misgivings because he pointed out that this was not a true quantum ground state. It didn't commute with the Hamiltonian. The staggered magnetization is not a conserved quantity. And And so he proposed a singlet state. And we'll be going back to that when we talk about spin liquids. Now, also, at the early part of the 20th century, we had the Bethe solution. Bethe showed beautifully how one could exactly solve the spin equals a half antiferromagnetic chain. And it was known not to have long-range order. It was known to have power law correlations. So many people felt that maybe, if one could philosophically extend this to higher dimensions, maybe we shouldn't have antiferromagnetism. Now, of course, everything changed with the advent of neutron scattering. And you've already heard about neutron scattering today in other contexts, but I want to remind you how much it changed the landscape for antiferromagnetism. Now, no one questions antiferromagnetism. So what was a crucial measurement? So what they did was they looked at this system, and they did neutron scattering. They did neutron scattering at high temperatures and at lower temperatures, okay, at 240 Kelvin and at 80 Kelvin. And you notice there are more neutron reflections as we go to lower temperature than there are higher temperature. They also did X-ray scattering. And what they found was that the elastic and the magnetic lattice were not the same. So neutron scattering became the method of choice for determining non-ferromagnetic spin-ordered states. But now we had a mystery, right? Because, and this is all part of the interplay between theory and experiment that has been going on in magnetism, particularly in frustrated magnetism, for a long time. And I hope to tell you more about that. Because we have a mystery. We've been told by the great Landau that the antiferromagnetic ground state is not the true ground state. And yet, neutron scattering tells us that we have an antiferromagnet. Okay. Well, enter Anderson and Kubo, and they set out to try and sort out this problem. And how did they sort out this problem? They said, let's develop a semi-classical theory. Okay? So let's ask, we know that the ground state is not truly the antiferromagnetic ground state, but let's ask how large the fluctuations are about this ground state. So what they did was, they took a semi-classical approach. They assumed that spins were like tops. They set them up as up, down, and then they looked at the zero-point fluctuations around those equilibrium positions. And what they basically developed, which is now called spin wave theory, is a sort of melting argument. This is like an equipartition argument. What they said was, they said, let's look at the change in the magnetization. We can write it as a Bose factor, okay, plus 1 over 2s times 1 over the dispersion. Now, in the classical case, the Bose factor goes as t over omega, so we get t over omega squared. In the quantum case, this is a constant, and we just have 1 over omega. So, let's just look at what that tells us. Okay, so what we're looking at is we're looking at expectation value of this. Now, for example, for d equals 1, what we said was, we said this goes as that, right, for quantum mechanics. Now, for d equals 1, our d dq up here goes as d over q. That's over omega. In these systems, omega goes like q. This is as q. And you see this is badly behaved. Okay? So that's consistent with what Bethe found. By contrast, if we put d squared here and look at 2d, this is quantum mechanics. If we look at 2d, we find this is q dq over q. This cancels, and this is well defined. Okay? So what this showed us, this very straightforward argument, was yes, it's not the ground state, but the zero-point fluctuations are small enough then the ordered state doesn't get destabilized. Now, interesting enough, for d equals 2, and of course for d equals 3, then we also have a stable Yale ground state. But d equals 1, we do not. So we're okay, because we're consistent with the Becher solution, and we're consistent with the experiment. Now, let me also remind you that for t equals 2, if we're interested in what's going on at finite temperatures, so this is classical, then following this will be d squared q, but now we have omega squared, so that's q squared, okay? And now again, we're going to have a problem. So that tells us that for the Néel ground state in 2 dimensions, at t equals 0 we're ordered, but at finite temperature we don't have order. Okay? But in 1 dimension we don't even have order at t equals 0. Okay? So Anderson and Kubo did this independently, and this was their way of understanding this discrepancy between what Landau said and what their experimental firms were showing. Okay? All right. Okay, now, I was lucky enough to spend summers at Bell Labs when I was growing up as an undergraduate and a graduate student, and there was a lot of folklore about Bell Labs, and perhaps I can share a little bit of that with you. In the heyday, which unfortunately was before I was a student, way before, in fact, even possibly even before I was born, but in any case, in the heyday, the theory group was run by a fellow called Conyers-Herring. Okay? And Conyers-Herring decided that it was very important to have people sharing offices who had very, very different styles. Okay? And in some sense, and he tried to get them to interact with each other. So Phil Anderson came, he worked with Ben Black, he came to Bell Labs, and he was put in office with Gregory Warnier. Now at the time, Phil Anderson has always been very impressionistic in his approach. Gregory Warnier, by contrast, was fascinated by Onsager's exact solution to the 2D Ising model, and was fascinated by what would happen if you had a frustrated system. Could he take the transfer matrix approach that Onsager had developed? And though I don't know of a paper that Anderson and Warnier wrote together, the interaction between the two will become evident as we discuss frustrated magnetism. So a take-home message from that is please talk to your office partner, whoever, you never know what can happen. So, okay, so frustration. So what do I mean by frustration in the spin context? Okay, in the spin context, frustration is easiest described with Ising spins. So let's consider Ising spins that are plus or minus 1, and let's say we have an antiferromagnetic interaction. That means we have the Néel state that isn't supposed to be there, but we know it is. Okay? All right. So suppose we have a square lattice, which is what Onsager did his wonderful solution of, which convinced many people that yes, phase transitions do exist theoretically and all of that stuff. Let's look at this triangular model. Triangular model, we have a problem. Okay? We have an unhappy spin. Why do we have an unhappy spin? Because with this Hamiltonian, which is a nearest neighbor Ising model, on the triangular lattice, in each plaquette, we have to have one unhappy spin. Another way of saying it is we always have one bad bond. It is not possible to simultaneously satisfy all terms in our Hamiltonian. Okay? On the square lattice, it's fine, but the triangular lattice is not. Okay? So the ground state condition is that we'll always have 2 up and 1 down, or 2 down and 1 up in each triangle. So all the interactions cannot be simultaneously satisfied, and we have one bad bond per plaquette. Okay? All right. So let's look at this a little bit more. Okay? We can actually order our system, and so for example, the way I've ordered this here, when I say order it, I can organize it, I guess is a better word. If you notice, I have this spin who has 3 happy bonds and 3 unhappy bonds. And you might ask, well, what happens at low temperatures? Okay? What's happening? Well, here's where the interaction between Anderson and Warnier becomes interesting. Wanye told Anderson that he was trying to understand whether this system had an extensive entropy based on the fact that it had these flippable spins. Back to this, you'll notice that here, if I flip the spin from up to down, I'll still have 3 happy bonds and 3 unhappy bonds. Okay? So that's what we call a flippable spin. This spin can do whatever it wants. It's not going to change the energy at all. Okay? All right. So Wanye was very interested in this problem, and in particular, he wanted to know whether it was possible to generalize Ansarger's solution to understand this problem. Okay? And what broke down in Ansarger's solution. The story was that he was working on this. This is Bell Lab's folklore. The story is that he was working on this, and Phil drew a picture on the blackboard. And the picture Phil drew on the blackboard is this picture here, where basically he's organized notice that we have hexagons, and in the center of each hexagon is what we call a maximally flippable spin. This is a spin that has 3 good and 3 bad bonds. I can flip this one, I can flip this one, I can flip this one, I can flip this one. And so Phil said, why are you doing all this work? I can just tell you what a lower bound on the entropy is. I'll take this state, and the entropy, this is per spin, is going to be basically kb over 3 log 2. Okay? Because it's going to come from counting the number of flippable spins. Okay? And that's, of course, going to be a lower bound because there are other states. So Phil drew this picture on the blackboard. That was it. All right. After a lot of really hard work, Wanye and Hutapo, who's across the ocean in Germany, actually calculated, because in this system you can enumerate the ground states, calculate the ground states. There's a finite entropy in the ground state. It's 0.323, this, which is only a tiny bit of entropy. Okay? All right. Now, one of the points that I want to make out of all this is a hallmark of frustrated systems is the fact that we have a large, sometimes extensive, as we have here, ground state degeneracy. Okay? And often, we have these local degrees of freedom, as we have here. I can flip the spin, nothing happens to everybody else. Okay? So that's a local degree of freedom. So we have a large ground state degeneracy, and that's something that we're going to see over and over again in a frustrated system. Now, what makes degenerate systems special? What makes frustrated systems special? Okay? Now here we're going to talk about Ising magnets because we can actually count states. Okay? If I look at the density of states of an unfrustrated magnet, here I have density of states versus energy, I usually have 1 ground state and maybe n excited states, etc., etc. However, if I look at the density of states of a frustrated magnet, such as the one we just looked at, the triangular antiferromagnet, first of all, I have to plot this as log of the density versus E, which means I have an exponential number of states, but I also have an exponential number of excited states, etc., etc. So in particular, the ground states can exhibit subtle correlations that's seen at low temperatures, and in particular, the degenerate ground state energy doesn't provide any energy scale, so all perturbations are strong. So we have a lot of instabilities. So we have very rich behavior, both in theory and experiment, but it tends to be hard because often perturbative methods don't work so well, okay, for exactly these reasons. Okay? All right. So let's switch gears for a moment and talk about continuous spins, because after all, most experimental systems aren't Ising systems. Okay? So let's talk about continuous spins. And here we can adapt a constraint approach that actually Maxwell made to understanding what kind of lattices are particularly good to study. So let me just erase this. So Maxwell made this to understand, made these kinds of arguments to understand elastic systems many years ago. And Rusner and Chalker, more recently, adapted them to spin systems. So let me just tell you what the basic idea is. So the basic idea is the following. Let's start with our Heisenberg model that we've been talking about. And we can rewrite this Heisenberg model in this way, where I have the sum of spins around each plaquette. want to know how to get ground state degeneracy. Now remember when you took linear algebra that if you had k equations for d variables, then the solution space was f equals d minus k. Okay, so in other words, if I have k equations, so I want f is equal to e minus k. Okay, so what do I have d variables and k constraints. Okay, so in other words, this is at the same notation. Oh, sorry, I have to change my notation. Here it was d. Okay, this way. So here it's d. So we're interested in, first we're going to look at the degeneracy for a plaquette. Then we're going to look at what happens when we go to the lattice. Okay, so d is going to be the ground state degeneracy. F is going to be the number of degrees of freedom, and K is going to be the ground state constraint. Okay? And what we're going to assume is that we have units of K spin, Q spins. So for example, for the triangular lattice, Q equals 3, for the pyrochlore, Q equals 4, etc. Okay? So we're going to do basically constraint counting. Now I should say this is an approximation. It assumes our constraints are independent and not mutually exclusive, but let's just try it. Okay? So let's just try it. So we're going to let's talk about Heisenberg spins. So for Heisenberg spins, we're going to assume that our spin length is fixed. So we have 2 degrees of freedom. Okay? So that means for each plaquette, for each unit, we're going to have 2 times Q. Okay? It's 2 for each spin, and we have Q in each unit. Okay? All right. Now we want to subtract K. But now K, our constraint is that we want the total spin to equal 0. Now, since we have Heisenberg spins, we have 3 components. So we have 2Q minus 3. And then we have to subtract the fact that we also have 3 global rotations. So we have another 3. Sorry, this is K. This is K, is 3. So D is equal to F minus K is 2Q minus 3, and then minus 3 for global rotations. Can you see in the back?
Yes.
Good. Please let me know if you can't see. Okay? And so what we have is 2Q over 6. Now, you see right away that if Q is equal to 4, then D is equal to 2. 2 times 4 minus 6 is 2. Okay?
2.
This is per plaquette. So right away, you see, and I could never draw this picture, that's why I'm putting it up here. You see that for a tetrahedron, we have 2 degrees of freedom per tetrahedron, per unit. Okay? Now we can extend this to the lattice. If we extend this to the lattice, basically we ask, what's the degeneracy of the lattice? Well, the degeneracy of the lattice, and let's take it for the tetrahedron, is going to be, in our case, it's going to be the degeneracy of each unit times n over 2.
Sorry, what's Q?
Q is the unit. So for example, I have Q equals 3 for it's the number of spins in a plaquette. Okay? So I have Q equals 3 for a triangle and Q equals 4 for a tetrahedron. Yes?
Okay. Can you use the mic?
Does the D add up?
Q, it's 2 times 4 minus 6. Right?
Okay.
This is 2. Sorry. Yeah. Thank you. Sorry. 2 times 4 minus 6. Sorry, I had it over here. I just had it erased. Okay? Good. Any other questions? Okay. So, the point is the following. What comes across in this is we want lattices that have a minimal number of constraints. And so corner sharing lattices are the lattices of choice to maximize degeneracy. Okay? Now, I want to emphasize, this is not the kind of degeneracy that you may have, it's what's called an accidental degeneracy. What's accidental about it? I can't take two states and by some symmetry get from one to the other. Okay? That's what I mean by accidental. All right? Yes?
Can you explain this approximation? The sound is
Yes.
Can you use the microphone so everybody can hear your question?
Sure. So you would like me to explain this approximation?
Yeah, because on the left, you have
Right.
And
So what I'm saying there, I think what you're asking about is the Heisenberg to that approximation? Yes. So what we're doing here is we're saying, look, we have the Heisenberg antiferromagnet. We're going to assume that we can write it as the sum of all spins around a particular plaquette. Okay? That's back to what I was saying about linear algebra. We're going to assume that we have independent constraints. Now, that may or may not be correct, but it's basically what we're saying is when we're counting degrees of freedom and constraint, it only works if you can assume they're independent but not mutually exclusive. And so that's part of the approximation that's going on here. Does that make sense? Okay. So the key thing here is, oh, sorry, this should be, I was 6, too much. Sorry, thank you. So the key thing here is when we do this very simple Maxwellian argument, the pyrochlore, which is a three-dimensional lattice of corner-sharing tetrahedra, is very promising because with this simple, this is a very simple constraint counting, good for the end of the day, I thought. Constraint counting, it tells us that this system is something that should have an extensive degeneracy for a Heisenberg space, and therefore something we should focus on. Okay? That's an interesting behavior. All right, are we good on this? Yes.
Maybe a silly question. So
No more saying it's a silly question.
So this big N entered because you went to the lattice.
Yes.
Correct?
Yes. So I wasn't very clear here.
So my question is the following.
This is basically, this is basically the number of spins, n, and the reason it's n over 2 is in this corner sharing system, the number of tetrahedra is is the number of spins divided by 2.
Okay, but in the lattice, it's not always going to end up being of the order of n. What is
Oh,
so
no.
special
It's
about
only for this. It's only for this corner sharing tetrahedra.
If it's the
this
triangle.
this is for the this is for the pyrochlore.
And if it's the triangular plaquette,
No, the triangular will not have this.
what's the degeneracy?
Actually, the triangular lattice does not have this kind of. It doesn't have an extensive degeneracy. Because remember, even the triangular lattice, even here, this is 0. Because Q, right? Q equals 3. So for here, D equals 2Q minus 6. I have Q equals 3. So then, per plaquette, I have no additional degree of freedom per plaquette, according to this argument. So what makes the pyrochlore special is that not only does it have Q equals 4, but it's corner sharing. Okay? This is a very simplistic argument. It's only to give a sense of, as I said, it only works if they're really independent, but it's just to give you a flavor for why the pyrochlore is special.
Do you know any other examples, or the degeneracy is very low?
In 3D, this is probably the best example. Kagame actually doesn't work so well in this system. It turns out that Kagame, well, actually, that's going to be my next picture. Kagame is here, okay? And certainly I've had a lot of interest in the Kagame. There's been a lot of interest. But with this constraint argument, the Kagame doesn't quite do as well. That doesn't mean it doesn't have an extensive degeneracy. It just means that it doesn't come out so easily, okay? And of course, one of the reasons I give you this is that normally for continuous spins, because they have fluctuations, we can't actually do counting the way we can for discrete spins. And that's why I wanted to give you this argument. And in some sense, the reason I'm giving you this argument is I want to motivate for you why we're going to talk about a pyrochlore lattice. Okay? Does that sort of answer your question? Okay. Does that answer your question? Okay. Yeah. For the Kagame, it's also a little bit more complicated because it depends. A Kagame is like a triangular lattice where you're removing one. So you would have to do this a little bit in a more complicated fashion. Okay. All right. Are there any other questions? Yes. No, go ahead. No, sorry.
Going back to the same question. So this is because it has these 3 global rotations. Is there any other case when you don't have like -6 and then the triangular case would give you some?
So here I have 2q minus 3 minus 3. I could also do it for x. By the way, I could also do it for xy, but then I wouldn't have 2. I would have 1. Right?
It never works
So
out.
right. So that's not so good. You see what I'm saying? Now I could do it if I'm interested in something with more components than a Heisenberg. It's not so physical, but I could get that too. The reason that the pyrochlore is special is it's something that we actually see in nature. Does that make sense? So it actually has a special place in this. And from this very simple argument, I hope you can see why there's been so much effort in these pyrochlore systems. Okay, any, pardon? Okay, all right, so what is the experimental signature? An experimental signature of a frustrated system is that I look at the inverse susceptibility. I have a local moment system. I look at the Curie-Weiss law at high temperatures, and here you see that I have this Curie-Weiss temperature. And the frustration parameter that was actually developed by Art Ramirez is when the ratio of the Curie-Weiss temperature over the Néel temperature is large. And you see in this region here, between the absolute value of the Curie-Weiss temperature and the Néel temperature, we have the possibility of something that was called by Mila a cooperative spin liquid. And we're going to be talking a lot about that. This is a system that is not completely disordered. It doesn't have exponential correlations, but it's not completely ordered either. Okay? So in that sense, it's like a liquid. Okay, so now I'd like to talk to you about spin ice. That sort of completes our introduction to frustration. Are there any questions about this before I continue? Okay, so I'm way over time, I guess. Okay, well, anyway, we'll keep on going. You've asked a lot of questions. We'll just keep on going. Okay, so back to Phil Anderson, 1956. Remember I told you that he had been talking to Gregory Wanier, and Gregory Wanier had been telling him about a beautiful paper by Linus Pauling. As you probably know, Linus Pauling is a chemist. Okay? And today, what I'm talking about is all about geometric frustration. You can also get frustration due to disorder, but we're going to assume that everything's very clean. Okay? So, Linus Pauling had been interested in ice because his colleague at Berkeley, Joke, had actually measured the entropy of ice. Liquid ice at atmospheric pressure, room temperature, well, not room temperature, at zero temperature, 0 Celsius, and, pardon? I said 0 Celsius, not 0 Kelvin. Anyway, zero at ice, we all know what ice is, and he found that there was an extensive entropy. So Linus Pauling had done a little calculation of this, and Wanier had told Anderson about it. Now, Anderson was very interested in magnetism. Remember, he was the fellow who, he was one of the people, he and Kubo were the people who convinced the theoretical community that, explained to the theoretical community how to reconcile Landau and the beautiful neutron experiments. Okay, so Anderson said he knew that there was something called spinels, which are pyrochlores. And as expected, most of them were Heisenberg spins, okay, because that's what happens in nature. One of the things he said, which is very interesting, and he wrote a little paper about this, he said, wouldn't it be great if we could get an Ising system on the pyrochlore lattice? Okay? Why would that be interesting? Because if we had an Ising system on the pyrochlore lattice, as we just discussed, we would write it in this way, and the energy would be minimized when the total spin per tetrahedra was 0. In this case, we would have 2 in and 2 out. Now, there would be a degeneracy for each tetrahedron. Remember, we have the constraint of 2 in and 2 out, and as we'll see, that's something very much motivated by Pauling's calculation. And this is a very nice cross-fertilization between ideas, not just between office mates, but Anderson was thinking about chemistry too. And for a single tetrahedra, well, we have 4 sites. This is a binomial coefficient. 4 sites, choose 2. That's 6. So we have 6 ground states. So what Anderson then said is he said, look, on a pyrochlore lattice, quarter-sharing tetrahedra, just as we've discussed, we would have the Pauling estimate of the ground state would be, well, we'd have Ising spins, so 2 to the n, and if you can see this 6 over 16 times the number of tetrahedra, n over 2, and so this is exactly the Pauling entropy. So what he said was, he said, Gregory one day kept telling him, oh, wouldn't it be great if we had a real system where we could look at these extensive entropies, okay? And Anderson said, if anyone can actually make an Ising system on this pyrochlore lattice, that would do it, okay? So, and he said this would be the entropy. And, all right. So how do we go for the mapping from ice to spin ice? Well, it turns out in ice, the oxygens are in hexagonal lattices, but the hydrogen bond, which has always been very mysterious to me, the hydrogen, what Pauling figured out is the hydrogen, you have 2 in and 2 out, which means that 2 of the hydrogens are close to the oxygens, 2 are far away. And you see that this paper was written in 1935. And what Pauling explained was that the entropy of water, frozen water, is actually finite and is exactly the value that we talked about before. Okay, so Anderson told Warnay, if anyone could make this, this is your system. All right. Well, this was 1956. Okay, so fast forward. And in 1997, Harris and Bramwell found 2 materials, dysprosium titanate and chromium titanate, which they believed to be the realization of Phil Anderson's and Linus Pauling's idea in spin systems. Now, 2 things. First of all, they went to very low temperatures, looked at the inverse susceptibility, and it did not order. Okay? Then the second thing, and this was a measurement done by Art Ramirez and in collaboration with Trio and Shastri, they measured the entropy, and in Monte Carlo as well. And the entropy of the system, and Art integrated up the specific heat from about 10 degrees down to 300 millikelvin, the entropy of the system was such that there was a residual entropy that was exactly within 5% minus Pauling's entropy. Okay. So that's pretty amazing. However, there's a rub. As always, the interplay between theory and experiment gets everybody to think. This system had no right to actually have this entropy. Why am I saying that? Well, first of all, one thing I didn't tell you was that when Mark Harris and Stephen Bramwell measured the inverse susceptibility of this system, the Curie temperature, that is if you extrapolate down, is ferromagnetic. Remember, ferromagnets aren't supposed to be frustrated. Second of all, there's a local strong crystal field anisotropy. Well, that's good news. That's what's giving us the Ising spin. So that's what's making the spins point in and out. Huge crystal field anisotropy. Okay? Crystal fields are basically due to the fields of the ions surrounding the spin. Okay? So that's good news. We have large spin, 15 halves for dysprosium, 8 for chromium. Where the classical limit, we've got a whopping big magnetic moment, 10 Bohr magnitude. Now, what's the problem with that? When we have large spin and large moment, that usually tells us that we've got dipole interactions. Everything I told you about the Andersonian argument was based on nearest neighbor interactions. But one of the big theoretical mysteries, which was a real tour de force to solve, was why is it that a system that has a ferromagnetic exchange, okay, we have crystal field anisotropy, But dipolar long-range interactions, why is it obeying? Why are they obeying the ice rules? Okay. So that I'm going to leave as a question. It was sorted out. Okay, and it was a tour de force in 2 different ways. It was sorted out. I don't think it's fully understood, but it was sorted out to some degree. I think what's understood now is why long-range dipolar interactions don't lead to ordering. And it has to do with the fact that you have effective screen. As far as I could tell in the literature, and I'm reporting to you because I haven't actually worked in this area, as far as I can tell in the literature, it's not completely understood why the ice rules work, but they do. Okay? One can make an effective model, but there are always some corrections, and everyone always argues the corrections are small, but I think the reason is always experiment. So this is a nice interplay between experiment and theory. All right. Yes? Sure. Yeah, he's here.
You mentioned about QRS temperature versus Aulian temperature, which is a measure of the fluctuation, right?
Yes.
But in a real system, as you mentioned, there is anisotropy. So if you measure it along different directions, they'll give you different QRS temperature.
That's absolutely true.
You mentioned also ferromagnetic QRS temperature of the system.
Yes.
Which direction was that? And if you measure different directions, will you?
That's actually completely correct. That what they did, I mean, when they measured the ferromagnetic exchange, well, here in each, the Curie rise temperature will depend on which direction you're in. Completely right on that. Here it turns out, going back to here, that here that for each tetrahedra, the spin either points out or points in. Okay, so it's a local axis. So you can't actually apply a field associated with all of them. Now, in this particular system, what they found was when they looked at high temperatures, at the inverse susceptibility in all directions at high temperatures, when they then extrapolated down to T equals 0, it was ferromagnetic. And what's interesting about that is, of course, we think of frustration as an inherently antiferromagnetic phenomenon. Here, what's providing the frustration is not the next nearest neighbor interaction. It's a competition between this huge, it's of order 200 Kelvin, crystal field anisotropy and the dipolar interactions. Okay. Is that, okay, thank you. Any other questions? All right. So, one of the questions is spin ice ordered or is it not? Why do I say, what's the problem? Well, there's no order as in a ferromagnet. It has an extensive degeneracy. But it's not disordered like a paramagnet. Remember, paramagnet is like a gas. It has exponential spin correlations. But here we have ice rules, which you can think of as a conservation law. And in fact, one of the questions you might ask, and this is something that's often asked in physics in general, is if we have a local constraint, does it have consequences at large distances? And here, the answer is yes. We can consider the moments as a sort of lattice flux field. Okay, so here, the role of the oxygens in our magnetic system are the centers of the tetrahedra. Okay, so if we have these arrows pointing the way the spins are, you see that for each center of a tetrahedra, I should have 2 in and 2 out. So the ice rules you can think of as telling you that the divergence of this artificial flux field, we're constructing an artificial magnetic field, artificial magnetostatics, is going to be 0. Okay? But now we can set up a gauge field. And we can take the simplest assumption, namely that we have a free field. And what's very nice here is that we have a local constraint, namely the ice rules, and what it exhibits then is an emergent gauge structure. Okay? And this is something that's happening all over the place in condensed matter physics right now. So this is an incredibly simple model, and yet we have this. So what you can do then is you can ask, all right, if I take this free field theory, can I then determine what the spin correlation should be. And that's what was calculated, and they found that they went as cosine squared theta. Theta is the angle that the spin has away from the direction it's supposed to be in due to the crystal field anisotropy over r cubed. And then what you can do is Fourier transform it over the lattice, the pyrochlore lattice, and make a prediction for neutron scattering to check whether these ice rules really work. And I would say they did pretty well. So this is experiment and this is theory. So in theory, you see that they have what they call these pinch points, okay, which are very well pronounced, very singular. In experiment, they're a little bit rounded, and you can actually see what the, if you will, the ice rule correlation length is about 200 angstroms, as they say in this paper. But the point is that the observation of these pinch points is a very nice confirmation of the local ice rules and the fact that we have this emergent gauge structure. Right? Okay, are there any questions? Now, we can even do more. Okay? When I say we, I'm talking in the collective sense, because as I mentioned, I haven't actually worked on this. Okay? Yes?
I have a question about.
Yes? Let's go back to this. Could you turn that on?
Hello?
Yeah.
Could you? I have a question about the pinch point. So seriously, they like predict that there's some divergence of the like approaching that pinch point. They have a different behavior, and this like cosine theta versus some r squared.
Yeah, they have to. What they did was they took this and then they Fourier transformed it. So of course, neutrons.
Yes.
You look at the momentum space. They Fourier transferred it using
k-space.
in k-space, and that's where they got the pinch points.
Yeah, and this series based on any like, is that nearest neighbor or the dipole approximation?
This is actually dipole. This is using dipole approximation. Okay.
Sure.
I thought we were running out of time, so I didn't actually. So what they've assumed, they have the spins as dipoles. And what it's actually, I'm going to give you a sense of that. There's something called the dumbbell model where they actually switch from spins to charges, and we're just about to get there. And that's actually how they calculated this.
Thank you.
Okay, and I'm going to give some references at the end if you want more detail, or we could also talk about it. But I think this is a very nice, this is a very nice agreement between theory and experiment to show that this local constraint leads to observable structures. All right, but now we've talked about a sort of artificial magnetostatics, but now we can actually ask, what are the excitations of this system? Because in many areas of condensed matter, when we have an emergent gauge structure, we get all kinds of interesting excitations. Okay? And so the question is, what's going on with excitations? Well, in spin ice, the obvious excitation is that you violate this 2-in, 2-out rule. So instead of having a spin like this, you flip it. And of course then, just like what we were talking about in the Ising system, and then what you end up with, two unhappy tetrahedron. Okay? Now, the idea of magnetic defects was actually discussed by a Russian physicist, and this came out in 2005. And he talked about magnetic relaxation in rare earth pyrochlores. Now, my friends who've been very generous with their view graphs, I should say, came out with a paper in 2008 called Magnetic Monopoles in Spin Ice. Okay, which title do you think got more publicity? Okay, there's a message here. All right, so what these are my friends, so so what happened actually, it's a sad story. The Russian fellow, from what I understand, he didn't put monopoles, but he put charges in his title. And the editorial staff at JTP, which is a Russian journal, they made him take it out. And so as a result, he actually did much of the same kind of my friends. They did it independently, but the point is that people didn't know about that. So there's a message here. All right, but as you must have seen, I mean, Claudio and Roderick and Shivaji have been enormously generous with their pictures and all that. They're good friends of mine. I want to keep, whatever, but there is a story there, and they do reference that. Okay, so what they're suggesting is that you actually can get magnetic charges in spin ice. Okay, so let's see how this works. What I'll do is I'll just give the main points, okay? So here we have spin, and what we're going to do is turn that into a dumbbell model. Dumbbell model means we take each dipole and we have a red and a blue, okay? Red and a blue. Now, at this point we've just changed from dipoles to charges, okay? And the charges are bound, right? Now, if we have two defects, like a red and a blue, okay? If we have an extra, if we violate this spin, two spin in, two spin out, we're going to have an extra thing of color like this, a source and a sink for our artificial magnetic field, okay? So that's what we have here. And the question that we need to ask is what happens when they pull this apart? Now, in one dimension, if you take sort of magnets all lined up like this, if you flip one dipole, it turns out you can pull them apart, okay? And the point is you can pull them apart and the energy is finite, okay? And that's what we call fractionalization. Why is it called fractionalization? Because the energy for each of those charges is going to be basically some fraction of a spin of a dipole flip, okay? And that happens in d equals 1 all the time. It's usually quite hard to have that happen at higher dimensions. And in fact, what we're going to see here is the first time that, to my knowledge, it's been seen in d equals 3. Just think about d equals 2. We're running out of time, so I can't go to the blackboard so much. But in d equals 2, if you try to do that, you'll find that your cost will go as L, well, not even d equals 2. Normally, your cost goes as L to the d minus 1. Okay? So in one dimension, you're fine, but in higher dimensions, your cost is going to diverge. And so you can't do that. Okay? Turns out on this lattice you can, and there's a very pretty dipole model that they came up with. Basically, because Raphael's standing here and I want you to be able to ask questions, let me just give you the gist of it. Okay, basically what they found was that the energy associated with moving these apart is finite. Okay? In particular, they have a magnetic Coulomb interaction, deconfined monopoles. The bad news is that the charge on these monopoles is minuscule. Okay? Now, do we have to rewrite what we know about electromagnetism? Of course, the answer is no. These are monopoles in H, not in D. Okay? So as a result, there's no violation. So in fact, what we have is we have a magnetic interaction, we have deconfined monopoles, we have a charge. There's no violation. The main reason we have no violation is because the defective tetrahedra tell us that the divergence of this is not 0, but of course we have H as well. So as a result, B is fine. So the key thing about all this is we have a rare instance of fractionalization in 3D. We have magnetic charges and networks of Dirac strings. Okay? We have sources and sinks of magnetic fields. Okay. People have been thinking about looking for these. You can do magnetic relaxation, but as far as I can tell, the results are somewhat controversial, and I've come to the end anyway. So what I do suggest, since I want you to ask some questions too, is here are some references if you're interested in further reading. I think you'll find this is a very nice article. In general, actually, this annual reviews of condensed matter physics I like very much because it's a very nice way of learning about areas that are, right now, it's available online, free. And I would recommend, if you're interested in learning more about spin ice, this one. This is also quite nice. This is in Science. This is before monopoles. And this is a general article on geometrical frustration. So thank you very much.
So you have us. We have some time for discussions now. Questions?
Yes?
In spin glasses that is disordered version of frustrated system, in general you have a linear specific heat at very low temperature.
Yes.
What kind of behavior you have in the specific heat of this material?
Yes, actually, well, of course, it depends on dimensionality in these materials. And this, one of the big areas that people are interested in is to look at spin glass behavior without disorder. So there are a number of systems like this, there's strontium garnet that's a Kagame system, where actually Art Ramirez has measured linear specific heat and there doesn't seem to be any disorder.
We want to know what the specific heat was in these specific systems.
In this system.
Yes.
Actually, most of the effort has, unfortunately, I didn't see anything at high enough temperatures because most of the effort was at very low temperatures with the entropy.
So which is the temperature dependence of the system at low temperature?
At low temperatures, I should know that. It's in this. I can tell you for next time. My guess is that it's linear, but I will have to look at that. I'll tell you for next time. Because the emphasis was always on integrating up the specific heat. I think it's linear. But that wasn't the emphasis in the actual write-up on this. It was always on the entropy. And in general, there isn't any specific rule in these frustrated systems about what the specific heat is. It's just not nailed. And perhaps that's partly because we're never really sure about the disorder situation.
More questions?
But I'll get back to you about that. Sorry that I don't know.
So you mentioned that a large degeneracy in the ground state is the hallmark of
Yes.
frustrated systems. But there are many systems that have that, so it can't be the defining state of frustration.
Absolutely.
Could you explain more about kind of how the kind of defining properties of the frustrated system?
So a frustrated system is usually one where you have competing interactions. So in this case, you have competing interactions either at the plaquette level or at the, you basically can't satisfy the energy, you can't optimize the energy of a plaquette. That's usually what it is in spin systems.
How does that differ from, say, quantum Hall systems where you just have a lot of ground state?
Okay, so, well, first of all, there are two types. Okay, I haven't even talked about frustration due to randomness. Here we're talking about periodic systems. In the two types of frustration we talked about here, one is over-constrained, one is under-constrained. The triangular lattice is over-constrained. So the point was that there was no way of satisfying every plaquette. The pyrochlore lattice was under-constrained, where we had extra degrees of freedom. One of the reasons I showed the density of states that I did is that that's very reminiscent of the quantum Hall effect. In fact, Bernard Mersner, who is the person who shared this slide with me, has worked a lot on the quantum Hall effect as well as frustrated systems. So there are some similarities.
In one of the figures you showed, there is something that reminds us of fractal behavior.
Fractal, okay.
Yeah. Do you know if the properties of a plaquette is observed in higher or bigger scales or sizes? Like the properties of magnetization for a plaquette?
Yes, I don't quite understand.
In bigger size, if it repeats, like if the fractal is only a the similarities is only a geometrical appearance, or the properties would repeat of a plaquette in bigger size or bigger scales?
I'm sorry, I'm not...
In all of the figures you showed, you can put it there.
Which one was this? Is this the
I believe it's for science.
Oh, from the neutron scattering?
Yeah.
Oh, okay. So the neutron scattering, this.
Yeah.
Maybe this one. well, this is in momentum space. So this is looking at the Fourier transform of a 1 over r cubed interaction, but Fourier transformed over using the reciprocal lattice vectors associated with the pyrochlore. Okay. So it's corner sharing, but I don't quite know how it's fractal. These are these so-called pinch points, which are associated also here. They're associated with the fact that we have those ice flows. But it's a local constraint, so I don't quite know what will happen beyond that. Okay, sorry that I can't answer better.
More questions?
Just in a square lattice, like Strassel copper borides, you can also sort of think about sort of frustration there to, let's say, study the ground state of the different.
Could you start again? I'm sorry.
Yes, yes. In the Strassel copper boride, which is a physical realization of spin liquid, two-dimensional system, is there any particular interest of inference of degrees of freedom of frustration in this systems? Do you have any comment?
Well, we're going to be talking about spin liquids.
Yes.
The last one, and in fact, frustration usually liquids. But basically, the idea is going to be that often you have quantum fluctuations plus frustration giving you some spin liquid behavior. So we'll get to that.
Okay. Yes.
Okay, but I'm glad you're interested in that. Okay, and I'll tell you about the low temperature specific heat background next time. Well, I'll tell you tonight, but I'm sorry I didn't. Okay, any other questions?
So I have one question. Maybe.
Sure.
It's a bit, I don't know if how much is known now, but is there any evidence for these magnetic monopoles? Experimental evidence.
Okay, I guess it depends who you ask, but since you asked me, I'm going to give you my opinion. There are plenty of fancy papers about it, okay? Let me tell you what the strategy is. The strategy is the following: to look at magnetic relaxation, as was in the Russian paper, and to pull out the energy and the charge of the magnetic monopole. Now, there was some beautiful numerical work that was done on this, and then the hope was to get this magnetic relaxation from muon spin resonance. Okay? And there are a number of glossy articles about this. Okay? However, the problem is that it looks like the muon spin resonance, which by the way fit the theory perfectly, it looks like it may not be due to what they thought it was due to. There are also neutron scattering experiments which suggest that they've seen these so-called strings. But one of my issues, and I should say these are my friends, one of my issues is I'm always worried when experimentalists confirm theoretical ideas where the theorists are part of the paper. Because there's proximity effect. Okay, so one of the reasons that I did not actually present that, I found the pinch points convincing, but one of the reasons, it wasn't just that I ran out of time, one of the reasons I didn't present that is when I read the muon spin resonance papers, the problem is there are all kinds of other possibilities for exactly the same effects, and the agreement was too good.
Maybe total.
Oh yeah, please. Oh, sorry. No, actually, you should comment on this. Stephen Bramwell's results. So did I express that?
Yeah, this was an unfortunate case in my opinion. Still, those original contributors do not concede or do not agree with criticism of not only me but all other universal people. But very short, just long story short, they didn't see the signal from the sample. They just picked up signals from surroundings and misinterpreted that as a signal from the sample, and cooked with very fancy theory, and said that they proved the existence of this fancy object. there are several errors in addition to that in a very simple interpretation procedure that probably any experienced graduate student in NMR or USR can tell. But unfortunately, they didn't have specialists in that 2 or 3 years of training. And all this is, so in my opinion, unfortunate incident. But that doesn't mean that the concept itself is invalid. The concept itself is very, very interesting. This only particular work was an unfortunate mistake. And also, this was done by Stephen Bramwell. Bramwell is a very nice person as well as a very brilliant scientist, as long as the neutron work is concerned. So somehow unfortunate error that he made. But this is a side story, I think, of everything. And so yeah.
Oh, that's not to me. Yeah, so that's why. Well, that's why I didn't show any of those results.
Okay, that often happens in physics.
Yes.
Nature publishes these wrong works.
Yeah, that's it. Don't believe, just because you see something in a glossy magazine, don't think it's right, okay?
About 20% of Nature papers wrong.
Right. So the point is that, that wasn't correct. One of the slides that I was going to show, but it's not, is the following, that you may know, the other point that I wanted to make is you might ask, you probably learned in particle physics that, or in quantum mechanics, that there's a real quest for a magnetic monopole. There's a Dirac quantization condition, and one of the reasons there's a quest for a Dirac monopole is because of the fact that one of the fundamental questions that we still don't understand is why is charge quantized? Now, it's very nice that my friends call this a monopole. It's a magnetic charge. There's nothing quantum mechanical about it. The charge is inversely related to the lattice spacing, which means that you can tune it continuously with pressure. I'm glad to say to those of you starting out in physics that the question of why charge is discrete is still waiting for you. Okay, this hasn't solved. So we don't need to rewrite ENM and all of that. This is a little bit of packaging. Okay?
I would like to know what are the applications of gravitation that you mentioned at the beginning of the lecture?
Oh, that you have to come to next lecture. Today we're just dealing with monopoles. Next lecture is gravity. Okay? I've got to keep you coming. All right? That's next time. I will talk about that, but that's next time. Okay? Here I wanted to tell you about these very nice results. Okay, so thank you very much.
Wait, well, you still have 10 minutes.
Sure. Okay.
Not off the hook yet. I actually have one, I'm not specialist either, so I remember that there was something about artificial spin ice, where they actually just use...
Yes.
So can you, do you know,
can
you tell us more about it?
Yes. So one of the issues here is that all the action in the system happens at 1 Kelvin, which is sometimes difficult to look at. And so one of the questions would be, could you actually make an artificial system, in particular a projected system, where you make a superconducting network, or something like that, and look at so-called artificial spin ice. It turns out, and the idea was supposed to be, could you catch these monopoles in artificial spin ice? I think they have made artificial spin ice. The ice rules are not as well defined, and unfortunately, monopoles are still free and wild. But yes, that has been done, and actually Roderick was involved with that.
I would like to ask about the relation between frustration and glassiness here.
Okay.
Do you have this multitude of ground states? Are they separated in phase space so that you have non-equilibrium, metastability, this kind of phenomenon?
Yes. So actually, that's a very interesting question. You have a very, very large number of states. And the question is, what happens, for example, as you reduce the temperature? Something that I didn't get to tell you about is that in this dysprosium and holmium system, you might say, what happens as T goes to 0? What happens is it freezes, it gets stuck. So you have many states, but not all the barriers are the same. And so one of the issues which I didn't get a chance to talk about, which is very interesting, is can you actually get glassiness in the absence of disorder? And for that to happen, you basically have to localize your system. And of course, if you have disorder, that's one way of thinning the system. But another would be that if somehow you could get the system such that it makes for itself very high barriers. So actually, that's an issue that people are, there are two issues, one of which we'll discuss, one of which we won't. Two issues that are very much open research areas is in these systems like spin ice, as you go to lower and lower temperatures, does it go out of equilibrium? Or can you, for example, get quantum spin ice? What would that mean? And this situation of going out of equilibrium then, of course, requires new kinds of techniques.
You didn't answer the question. Because is the distribution barrier height similar in pure systems like this, disordered classes that Muccio is referring to?
Okay, now,
so I think we should push.
Okay, the point is it depends on the frustrated system. For example, I've, in an effort to study glassiness in the absence of disorder, I've studied a mean field system where by construction all the barriers scaled like n. Okay, then that's very similar to a spin glass. But it wasn't nearest neighbor interaction, it was a long range system. I think the answer to that depends very much on the details of the model. And certainly there's been a lot of work, particularly in Paris and in Rome, on looking at mean field models that don't have disorder, that seem to go out of equilibrium. But it's very, very tough to make a system without disorder that doesn't have low barriers. So for example, I think next time, maybe next time or the time after, I'm going to talk about a system where we can actually count the number of states. And it definitely doesn't order. We can show it doesn't order. But there, it definitely does not go glassy because the barriers are very small. The problem in these kinds of systems, if you have local spin flips, the barriers are going to be small. Of course, the barriers are usually related to how many spin flips you need to get between states.
Hi, so you mentioned that for the case of dysprosium compound, the crystal field splitting is important,
yes,
right?
Very important.
So my question is that possible that you have frustration just because you have comparable energy scales of J in crystal fields and different kinds of anisotropy between the different doublets, and you don't need geometric frustration, just competing interaction between the crystal field schemes?
Well, in fact, I think you've summed up exactly the situation. We don't have geometric frustration in the usual sense. We have geometric frustration in the frustration we usually think of as unhappiness. Here, what we have is the competition between the dipolar and the crystal field anisotropy, which is very large, means that for each tetrahedra you want 2 in and 2 out, and there are many ways of doing that. So we almost have over happiness, and so
okay.
Over satisfaction. And the nearest neighbor interaction doesn't play a role the way it did earlier. Here we have degeneracy.
In principle, you can have that in
Yes.
any low symmetry system.
One of the interesting things about the spin ice, it was motivated by Anderson's original suggestion, but it's actually not frustrated in the usual sense. It's a ferromagnetic system, but it's the crystal field anisotropy versus the dipolar that's giving you the competing interaction.
Thank you.
Does that, so exactly what you said. And actually, I think they just found a third compound now, but these are the two.
Any more questions? Okay, so let's thank Premi again.